So welcome back. Let's continue our discussion of the blood oxygenator. So we have this ramp, we have fluid trickling down the ramp, and we're looking to derive this velocity profile. We started this problem in the last lecture, and we broke it down into a bunch of parts. The first step was to select and define an appropriate shell, which we did. There were some strategies associated with defining that, including like which dimensions we choose as our deltas, etc. Last time we applied conservation of mass to the shell, and this ended up affirming that the flow was indeed 1D, that we basically had flow only in the x direction, and that flow varied only in the y direction. And we got there with applying conservation of mass to this little shell with a width delta x and a height delta y that was completely contained within the depth of the fluid. So we ended up affirming that our x velocity is a function of y. So what are we going to do for the rest of this lecture? Well, we're going to eventually get to our ultimate goals of deriving a velocity profile, x velocity as a function of y. Then once we have this velocity profile, we'll end up figuring out what is the shear stress distribution within this fluid, right? And shear stress being important for determining whether the blood is damaged with the from the flow through the oxygenator. And we'll also be able to determine the volumetric flow rate, as a function of some of these problem parameters. For example, like if I had a film of a various thickness, how fast would the pump need to pump the fluid up to the top of the oxygenator in order to achieve that flow? So these are things that we care about. So what's the next step? Next step now is to apply conservation of momentum to this shell. This is going to set up a differential equation, and spoiler alert, we're going to need conservation of momentum both in x and y. So let's get started. So if we're going to apply conservation of momentum, let's go ahead and apply it. And I'm just going to keep it in the vector form. It'll save us a little bit of work later, so bear with me. So conservation of momentum, on the left-hand side, we have the time derivative of the integral over the volume of our vector velocity times density dv. And that's equal to the right-hand side, which we have negative an integral over the surface of vector velocity times density times v dot n dA. And this is our ins and outs for momentum. And then our momentum generation is the sum of forces. And these, of course, would be vector forces if we're dealing with the vector version of conservation of momentum, of external forces. Now, take a moment now and pause and ponder. For this particular problem that we're working on, what should this left-hand side be? All right, well, perhaps you've paused and pondered now. We said we were dealing with a steady flow of blood down this ramp. So, we're not all of a sudden, pumping a little bit and then all of a sudden ramping up how much we're pumping down. If we're assuming that we're in steady state here, so this term on the left-hand side is basically going to be 0 because we're steady. Now, take a moment, pause and ponder. Consider what this term is going to be for this problem. All right, well, we like to think of this problem as the ins and outs, right? So if I think about my little chunk of fluid, I have some velocity going in to one face. I have some velocity going in the outer face. I don't have any velocities crossing these faces or coming in at weird angles like this. So if I think of my ins minus my outs for this whole thing right here, well, we said that velocity doesn't vary in the x direction. So whatever I have here and whatever I have here must be the same. So yes, I have some momentum entering, yes, I have some momentum exiting, but if they're the same momentum entering and exiting, the ins and outs basically perfectly cancel out. So this ends up going away because our flow doesn't vary with x. So we basically have the same momentum entering and exiting. So ins and outs happen to cancel for this problem. So what does this mean? This means for both x and y momentum, we're essentially just balancing forces, right? So we're just balancing forces. And of course, you know, if we think back to problems that we solved in mechanics, if we had something just trucking along at constant velocity, that was essentially the same as a statics problem. You know, if things aren't accelerating, then all forces on them must be equal, right? So if we don't have this time derivative of velocity business going on, nor do we have momentum changes going in and out, then basically forces on our little chunk of fluid must be balanced. So historically, when we've talked about these external forces on control volumes, we've broken up these into 4 flavors. You can look back in your notes, pause and ponder now if you care to try to recall them yourself. But here they are. They're the force of gravity, the forces due to pressure, forces due to shear stress, and forces that are through solids that cross the control volume. So pause and ponder now. Are there any of these for this that we can just get rid of right away? So perhaps you've paused and pondered. Well, there are no fluids, or there are no solids that cross our control volume, right? So we basically defined this little chunk of fluid. We defined this control volume to be completely contained within the fluid part of our oxygenator. So if this little chunk of fluid, the control volume associated with it, is entirely within the fluids, then we can cancel out this. So what do we need to do? We just need to figure out what these 3 forces are, and in particular what the x and y versions of these, or the x and y components of these 3 forces are, and we'll balance them on this control volume, and we'll balance them both in x and y. So let's do the easy one first. Let's talk about gravity now. So pause and ponder. What is the x component of the gravitational force on this chunk of fluid, and what is the y component of this gravitational force on the chunk of fluid? So let's figure out Fx gravitational and Fy gravitational. All right, well, perhaps you've done it. Right? If we think about this fluid, I think gravity's pulling down like this. But if you remember, we defined our coordinate system x to basically be going down the ramp and y to be perpendicular from the ramp. So in this case, if gravity's sort of pulling vertically, there is going to be some component of gravity in the y direction and some component of gravity in the x direction. So we can't get rid of either of them. If you look back at the geometry of the problem, we're given this angle alpha, and we know that gravity is pointing down like this. So we're going to know essentially gravity is going to have some component in the x direction and some component, I guess, that points in the minus y direction. So those will help inform our gravitational forces here. In general, if you dust off your mechanics notes, we know that the magnitude of a gravitational force is mg, and then if we take a component of it, we're going to need a sine or a cosine of alpha. In this case, the mass of this chunk of fluid would be given basically by the density, which we assumed was some known constant, and we'd also need to multiply that density by the volume of the shell to basically get its mass. So we can basically take density, multiply it by the shell volume, multiply it by g, take a sine or a cosine of alpha, think about whether it's plus or minus, and then that will give us these gravitational forces. So here they are. The x gravitational force is going to be g sine alpha times density times W times delta X times delta Y. Where this is the volume, multiply the volume by density to get the mass, multiply that by G, but take just the X component of that. And then for the Y component, we get minus G cosine alpha times density times W times delta X times delta Y, where again, we have the mass, or the volume times density gives us mass. G cosine alpha is the Y component of that, and then we have a minus sign here to basically indicate that the Y component of that gravity points in the minus Y direction. So we've now squared away our two components of the gravitational force. Let's now move on to pressure. So if I'm thinking about pressure, I want to draw my little box. And we know that pressure is defined to act inwards on surfaces. And we're basically going to pull a similar trick to what we did last time when we were talking about velocity, where we can shrink these small enough so we assume pressure doesn't vary across these surfaces, but pressure could hypothetically vary from one surface to another. And we could sort of apply the same trick to these top and bottom surfaces as well. So we're basically going to say, hey, we have some position here, x, some position here, x plus delta x. And then at the bottom, we're at some position y. And then at the top, we're at some position y plus delta y. And we're going to think about these forces, and if we have imbalances in the pressures on these surfaces, then we could perhaps get a net pressure force from that. So we can use this idea to help formulate the x component of the pressure, the x component of the pressure force. Well, we have whatever pressure we have at x times the area of this face, and we know the area of this face would be delta y times w. So in general, we know force equals pressure times area. So here we're talking about this face, this upstream face right here. And this pressure pushes us in the positive x direction, so we have positive out front. But then we have this force that's pushing us at x plus delta x. So that force would be minus pressure at x plus delta x times delta y times w, where the area of this face is delta y times w. And these forces don't contribute to forces in the x direction at all. We can formulate a similar thing for y pressure forces. So what's that going to look like? Fy due to pressure is equal to the pressure at y times delta x times w minus the pressure at y plus delta y times delta x times w. And now we've formulated both our x and y pressure forces. So what can we do? We've checked this off. Great. So now we've completed gravitational, we've completed pressure. We know that there aren't any through solids forces. So now all we need to do is formulate the force due to shear stress on this control volume, and we'll have squared away all of our forces. We can then equate the x, all of the x, or we can equate the sum of the x components to 0, then we can equate the sum of the y components to 0, and hopefully that will get us closer towards solving this, this unknown velocity profile. So now let's work on this shear stress force a little bit. So imagine my little chunk of fluid. We know that the way, if we use our positive convention for shear stress that this textbook uses, we know that there's some shear stress that acts in one direction on the top of the fluid, and sort of by convention it acts leftwards on the top and acts to the right on the bottom. But these two shear stresses don't necessarily need to be equal to one on another, right? So we could hypothetically have more shear stress on the top than on the bottom for this chunk of fluid. Pause and ponder now. Do we have any shear stress on these faces? So take a moment, pause and ponder. Do we have any shear stress on these faces? Well, the answer for these faces is no. And in order for us to have shear stress on these faces, we would need velocity gradients in this direction. So we would need a y velocity and a y velocity that varied with x in order to have shear stress on these faces. So we don't even have a y velocity at all. So so there's no shear stress on these faces, right? We would need fluid sort of fast fluid here and slower fluid here in order to get shear stress on this face, and similarly on this face as well, right? So there's not even any velocity moving in this direction, so we can't have any shear stress on these two faces. So what does this mean? Well, the implication of this is that the force in y due to shear stress is going to be equal to 0, because the shear stress on these faces can only act in the x direction. So that basically means there's no y force due to shear stress. And we can formulate our x force due to shear stress. We can formulate that as following. Well, we know that shear stress is equal to force times area. We can basically say, hey, all right, there's some position y right here. There's some position y plus delta y right there. These don't necessarily have to be the same as one another. So if you recall that shear stress is equal, or force is equal to shear stress times area, and we recall the area of this top face is delta x times w, the direction into the page, then we get the following. So the shear stress is basically minus tau yx at y plus delta y minus tau yx at y times delta x times w, where that one came from here and this one came from here. And I just sort of did some factoring out of some common factors and a minus sign just to make our lives a little bit easier in just a moment. So what does this mean? We now have an expression for our net gravitational forces for x and y, our net pressure forces for x and y, and our net shear stress forces for x and y as well. So we're going to now collect all the x components, collect all the y components, and set them equal to 0, because we determined earlier from conservation of momentum that the sum of forces is 0. So let's go ahead and do that. All right, so putting all this stuff together, here we have it. For x, we have 0 is equal to g sine alpha times rho times w times delta x delta y plus p at x minus p at x plus delta x times w times delta y minus tau yx at y plus delta y minus tau yx at y times w times delta x. Just barely on one line. Now, for our next, for y, we have 0 equals minus g cosine alpha times rho times w times delta x delta y plus p at y minus p at y plus delta y times w times delta x. All right, and that's it. And remember, there is no shear stress term for the y. All right, so, all right. Well, we can start making a little bit of progress here. Now remember, what was a trick we pulled with conservation of mass once we got to kind of these big messy equations with a bunch of deltas and, you know, some differences between things? Well, a trick we did was we divided by shell volume, which was delta x, delta y, w. All right, so when you divide by shell volume for your x, you get 0 equals rho g sine alpha minus, and I'm gonna switch this order a little bit right here. Pressure at x plus delta x minus pressure at x divided by delta x minus tau yx at y plus delta y minus tau yx at y divided by delta y. And then for y, we get something even a little bit simpler. We get minus g cosine alpha rho minus p at y plus delta y minus p at y divided by delta y. All right, then we have our things right here. We can take limits as the deltas go to 0, and remember, because these things could hypothetically, you know, for example, pressure could, for example, be a function both of x and y. You know, hypothetically, these things could vary both in x and y. These things start to look like derivatives, but remember, because these things could be functions of multiple variables, we want to replace these things not with ordinary derivatives, but with partial derivatives. Replace, you know, something minus something over delta something with partial derivatives. So what is that going to look like for x and for y? Well, for x, we're going to have, you know, this term is basically unaffected. So we still have 0 equals rho g sine alpha. This term, you know, we have a minus right here. This first term, this is essentially a derivative of pressure with respect to x. So we get partial pressure, partial x. And then the second term right here is a derivative of shear stress with respect to y. So we get d tau yx dy. The second, and then for y, we have minus g cosine alpha times rho, and then we have partial pressure with respect to y. All right, so what have we done? We've gotten ourselves a pair of differential equations. It's differential equations that have both x and y as independent variables, and both p and shear stress, both pressure and shear stress, as dependent variables. So this is going to be a bit of a mess to solve. Oof, yikes. So this is going to be a little bit tricky. So we might need to be a little strategic about how we solve this. So anytime I get some pair of differential equations that I need to solve, I usually like to try to start with the one that's a little simpler. And if I can make progress in the one that's perhaps a little bit simpler, then I might be able to plug that in to the more complicated one and then get something that I can deal with later. So we're going to start with this one, see if we can solve this one, or at least make some progress. And then, for example, if we got some information about pressure, that might help us resolve this such that, then I could get x, make a little bit more progress with my x equation. So this is the plan. We're going to start with this one. All right, so starting with the differential equation that we got from y momentum, we can try to start solving this. So I'm just going to bring this guy over to the left-hand side, and then if it's a differential equation, well, perhaps we could solve this differential equation by integrating it, right? So what could I do? I could basically integrate dp dy. I could multiply both sides by dy. So I can integrate both sides of this equation. When I integrate the left-hand side, well, if you integrate a derivative of something, d that thing, then you just end up with pressure. And then when you integrate the right-hand side, well, all of these are constants with respect to y. So when I integrate the right-hand side, I get g cosine alpha rho. So pause and ponder. Have I done everything? Is that it? Is this the whole story? Oh, sorry. Well, definitely not, right? When I integrate a constant with respect to y, I get, you integrate a constant with respect to y, you get that constant. So now, pause and ponder. Have I done everything right here? Well, some of you who would be dusting off the high school calculus might be like, hey, wait a second. When you integrate this thing, when you integrate something like this, when you integrate something, you get plus c. And if you were integrating ordinary derivatives, that would be correct, right? If you integrate something, if you have indefinite integrals and you integrate it, you get plus a constant. It's a different story with partial derivatives, though. With partial derivatives, you don't get a plus c. Rather, you get plus a function of any other variables that that this thing could depend on, right? So what you get is not plus c, but you get plus a function of all variables except for the one that this was a partial derivative with respect to. And this function is something that's as of yet unknown. So instead of getting a constant of integration, when you have partial derivatives, you get a function of integration, and it's a function of all of the variables with respect to y. Why is it a function? Well, you can imagine if I take a partial derivative of this function of all variables except for y, if I take a partial derivative of this with respect to y, it appears to be, with respect to y anyway, just like a constant would be, because you're taking partial derivatives, you treat everything else like a constant. So what does this mean? We have pressure, but it's this, we have this kind of messy, like, all variables except for y. And what do I mean all variables except for y? I mean problem parameters, but also, this could be like x, z, and t as well. So let's think if we can make any progress here. Well, we already know that it's not going to be a function of t. Why is it not a function of t? Because we assumed it was steady. We also assumed that there's no z variation in this problem. So, we've at least made a little bit of progress. It's a function, could be a function of x, z, and t. We concluded that it's not a function of z or t, but hypothetically it still could be a function of x. So let's see what this function of x might be. So let's try to figure out what this as of yet unknown function of x could be. Well, when you're trying to, when you integrate something and you get constants of integration, or in this case functions of integration, what information do we have to sort of help us deal with this thing right here? Well, we have what information at our disposal for figuring out f of x comes from boundary conditions. And what do I mean by boundary conditions? Well, by boundary conditions, I mean parts of the flow where we know what's going on. Right? So for example, one part of the flow where we might know what's going on is like the surface of the flow, or the bottom of the flow, or something like this, right? So what do I mean? Parts of the flow we know what's going on. We know what's going on right here. You know, right at the surface of this blood, what's the pressure right here? Well, we know it's got to be atmospheric pressure right here, right? Right at the surface right here, it's got to be atmospheric pressure. So this might be able to help us figure out f of x. So put a little more rigorously, we can say that the pressure, if we take this pressure function and evaluate it at y equals h, then it's gotta equal atmospheric pressure. Because we basically said, hey, at the surface of the blood, you know, all of that surface of the blood is just exposed to atmospheric pressure. So at y equals h, this whole expression for pressure has to be equal to atmospheric pressure. So we can then set that equal to this if we evaluate it at y equals h. So what does that mean? We get minus g cosine alpha rho h, where we've subbed in at y equals h, plus our as of yet unknown function of x. Now, what does this mean? Well, we can solve this for f of x, and we can basically say f of x has got to be equal to atmospheric pressure plus g cosine alpha rho h. We can now take this f of x and we can sub it back in. We could take this expression and sub it back in. And interestingly enough, this f of x turns out actually to not be a function of x at all, but rather a constant. So I guess we could have been okay with a plus c here, but you know, that's not always going to work, right? So in this case, our f of x is this right here. So what does this mean? We can sub in this f of x right here. Now that means we have pressure entirely in terms of known constants, and that might help us make progress towards our x momentum equation right here. So pressure is equal to minus g cosine alpha times rho times y minus h. Or if you wanted to put this a little more compactly, we could say y equals rho g cosine alpha h minus y. And this actually turns out to basically be hydrostatic. So even though sometimes fluids move, you know, under some circumstances you can still get the equivalent of hydrostatic pressure, even if the fluid is moving. Oh, silly me. I forgot atmospheric pressure on both of these terms. Sorry, forgot to carry that through. Success. All right, so this is, you know, this is essentially hydrostatic pressure right here. So what does this mean? We can basically take this and we can sub this back into, we can sub this into our x momentum equation to see how much progress we get. So if I want to take pressure, if I want to take this pressure equation and sub it into x momentum, pause and ponder. What do I get for my x momentum equation once I sub this expression for pressure in here? Well, what's the key giveaway here? Do I see any x's anywhere in here? No x's. No x's, interestingly enough. No, that's not a comment on my relationships. No x's in this expression here. So when I take this pressure and sub it in, the partial derivative with respect to x of this whole expression is going to be 0 because x is treating all these like constants. So if I take this partial derivative with respect to x, what does that give me? 0 equals rho g sine alpha minus 0 minus d tau yx dy. So now I have an even more manageable differential equation here. So now let's see what kind of progress we can make with this. So I'm going to see, ultimately our goal is to figure out velocity profiles, but first I'm going to see what progress we can make on this shear stress equation. So what is this going to look like? Well, I'm going to bring this over to the left-hand side. So I can basically have partial tau yx dy is equal to rho g sine alpha. I can multiply both sides by a dy, and I can integrate both sides as indefinite integrals. When I integrate the left-hand side, I end up with tau yx. When I integrate the right-hand side, I have rho g sine alpha times y plus, well, what do I get here? These are indefinite integrals, and here's an integral with a partial derivative. So pause and ponder. What should be this thing here? Well, hopefully you've paused and pondered. It's going to be not plus c, some constant, but rather some as of yet unknown function. And I'm going to give it a different name. So the previous one we called f of x. This one I'm going to call g of x to distinguish that it's some different function than this f of x that we got before, right? So, you know, it's going to be some different function. So here we have it. So what do we have here? Well, we now need to figure out, you know, what sort of boundary conditions, right? We can resolve this via boundary conditions. What kind of boundary conditions do we have on shear stress? Well, let's dig out our diagram for the flow system, and let's think, you know, where do we have information on shear stress right here? Well, if I think about it, the blood that's at the very top of this surface here is basically in contact with air, and the air can't provide hardly any resistance to this flow moving around, right? So tau yx evaluated on the surface has got to be equal to 0, right? We got to basically say, hey, there's no shear stress on the surface. There's nothing there here to hold back this top surface of the flow right here. So basically the air, you know, the air that this flow is in adjacent to, basically can't apply any appreciable amount of shear stress to that surface right here. So there's definitely going to be shear stress down here in the depths of the fluid, but this layer right at the top, no shear stress right there. So what does this mean? Put a little bit more formally, we'd say tau yx evaluated at y equals h has got to be equal to 0. And this is going to help us sub in, this is going to help us resolve this as of yet unknown g of x. So what does it mean? Well, we end up with, when we have this expression, we end up with rho g sine alpha h plus g of x needs to be equal to 0. What does that mean? We basically have this right here. Oh, I guess behind the scenes, I said this g of x. This g of x hypothetically could be a function of, this could be a g of x, z, and t, but for the same two arguments that we made earlier, steady and no z variation, we got rid of this, right? So now we have it right here. So we have this boundary condition right here that's going to help us resolve this g of x. What do we find out right here? Well, we basically say g of x has got to be equal to minus rho g sine alpha times h. And this gives us all the information to now we can treat g here. So what does this mean? We can basically plug in this expression for g, and it turns out that g actually isn't a function of x at all. It's just this constant that we can plug in here for tau by x. So we have tau yx is now equal to rho g, sorry, to get my color coding straight, it's going to be equal to rho g sine alpha times y minus h. And we have that right here. Awesome. So now we have an expression for tau yx. But, Professor Landon, you might say, our whole deal here was to try to get a velocity profile, but all you've done is got us an expression for shear stress. How is this going to be helpful? Well, stay tuned for the next step. So, how do we bring velocity into the mix? Well, we want to think about what our next step for solving. I want to think about what our next step for solving these things are. So, we just finished applying conservation of momentum. We did x and y, and we ended up setting a differential equation. We solved some of it, but there was sort of a limit to how far we could go. And ultimately, what our goal is to figure out a velocity profile, not some expression for shear stress. But we can start bringing in velocity into the mix if we apply some constitutive relationship. So we said we were going to assume that this blood was Newtonian, and if we apply the Newtonian constitutive relationship for fluids, then we'll bring in a differential equation for velocity. So what's that going to look like? Well, for Newtonian, if we assume Newtonian, then tau yx is going to be equal to the following. So tau yx is equal to minus mu times dvx dy. And strictly speaking, these are partial derivatives, but we can we could sort of proceed in the same way with solving partial differential equations that we did earlier, or an alternative to doing the partial derivative business that we did earlier is if we said, hey, Vx hypothetically could be a function of x, y, z, or time. We already, Vx could be a function of all these things. We said it was steady, so it's not a function of t. We said there was no z variation from just one of our problem statements, basically, assuming that the flow at any plane, at any point, in this direction is not varying. And then from conservation of mass, we safely concluded that Vx was not a function of x also. So what does this mean? Vx is a function of y only, and anytime you have partial derivatives where you conclude that the thing is a function of only one, you can replace these partial derivatives with ordinaries. So this reasoning here, we can basically say, hey, we now have ordinary derivatives over here. So what does this mean? We can now basically say minus mu times dvx dy is equal to rho g sine alpha times y minus h. And let's see if we can solve this differential equation. Next up, velocity profile. Let's proceed. So I'm just going to move mu over to this side and separate variables and integrate. So I integrate the left-hand side, I get Vx, I get integral dvx, and then on the right-hand side, I I'd get minus rho g sine alpha over mu. I can go ahead and pull those things straight out of the integral because I know that they're constants, and then I get y minus h dy. I can integrate both sides, and in this case, and now I have dvx, or integral of dvx just becomes vx. Now I have minus rho g sine alpha over mu. I integrate the right-hand side, and I get 1/2 y squared minus yh. And, I could attempt to try to put limits of integration on these. For these types of problems, I think it's usually a little easier to put constants of integration and find them later. So here I integrate. In this case, I actually do have a constant of integration because the original derivative that I had was an ordinary derivative as opposed to a partial derivative. So when I integrate ordinary derivatives, I get a constant of integration as opposed to a function of integration that we had earlier. So what do we have it here? So we have this Vx. How do I go about finding this constant of integration? I can do this via a boundary condition. So take a moment now, pause and ponder. What boundary condition is going to help us resolve this as of yet unknown constant of integration? Well, perhaps you've thought of it. The flow velocity right here at the base of the plate should be 0. So our x velocity evaluated at y equals 0 is going to be equal to 0. So let me write that out a little larger and more mathematically. So our x velocity evaluated at y equals 0 is going to be equal to 0. And that's basically saying the molecules of blood right above the non-moving plate are also not moving. So what does that look like? We get 0 equals, and then we get minus rho g sine alpha over mu. We sub in y equals 0, and we basically just get 0 minus 0 right here, and we get our plus c. So what do we conclude? We got to conclude that c equals 0. So we conclude that this equals 0. We can then sub 0 back in this equation, and we can get our x velocity. And if you were to go ahead and plot that, I'll spare you the details of it. But if you were to go ahead and plot it, it would look like this. Where the max velocity occurs right here at the surface. Why does the max velocity occur right here at the surface? Well, right at the surface, there is no shear stress, which basically means there's no velocity gradient right at the surface. And if there's no velocity gradient, then we're basically reaching our maximum velocity right here. There's 0 velocity down here, right? So we can check, we can check at y equals 0, you get 0. If you were to take the maximum, you would get the maximum right here at y equals h if you were to plot that. So we get basically dvx dy evaluated at y equals h is equal to 0 because there's no shear stress at the surface, and also that basically implies the max velocity is right here at the surface, which is pretty cool. What's another sanity check that we should do? Well, probably another sanity check that we should do is we should check units, right? Baby you know who. Baby you know who is a real stickler for units, so we want to make sure that she's happy. So left-hand side, Left-hand side's got to be meters per second. Hopefully this equals the right-hand side. Density is kilograms per meter cubed. G is meter per second squared. Sine alpha is unitless. Viscosity is kilograms per meter second. And y squared or y times h, those are both meters squared. So crossing my fingers, let's hope a lot of this stuff cancels out. So my meters, meters squared, and meters cubed, those all cancel with one another. My kilograms cancels with kilograms. And then at this point I have 1 over seconds in the numerator, or 1 over seconds squared in the numerator over 1 over meters second in the denominator. So I can multiply by meters over meters. Those cancel. And then 1 of the seconds, this 1 over seconds and 1 of the 1 over seconds squared in the numerator cancel, and I'm left with meters per second. Whew. Success. All right, so 2 simple sanity checks. One sanity check is like, does this profile make sense? And the answer is, yeah, it makes sense right here, it makes sense right here. And then another sanity check, do the units all line up? All of this lines up. Success. So what's another thing that we wanted to do? Well, I would say we successfully derived our velocity profile. We have our distribution of shear stress in the film of blood. Well, actually, we kind of got number 2 for free on the way, right? If you look back to the expression that we had for shear stress earlier, we already got our shear stress distribution. So take a moment now, pause and ponder. Where is shear stress the highest? Well, shear stress is highest, well, I guess highest in magnitude. So where's the magnitude of shear stress the highest? Well, the magnitude of shear stress is highest when this part of the expression is smallest. So if we basically sub in y equals 0, we get the highest amount of shear stress in terms of magnitude. And so what does that mean? We basically need to be worried about that blood clotting or the the tearing open of the platelets and all that stuff right at the bottom of the plate. And what does that mean? Well, basically it's the bottom of the plate that's kind of holding back the whole chunk of fluid above it, whereas fluid just below the surface only needs to hold back a couple of molecules, right? Whereas fluid at the bottom is essentially holding the weight of that whole fluid on top of it. So we essentially, just in accomplishing step 1, also fulfilled this goal of step 2. If we didn't already come across this this shear stress equation explicitly, then we could always take our velocity profile and sub it back into the Newtonian relationship, the dvx dy, in order to get a shear stress profile. But I digress. Finally, we can do the volumetric flow rate. So we can use our brand new velocity profile to figure out a volumetric flow rate, where we basically have some flow going down. We have our brand new velocity profile coming out the exit, and we have some volumetric flow rate going in. And I'll skip the details, but if we did a macro control volume for this thing for conservation of mass, and we essentially imagined it going some distance w into the page, right? I'm trying to draw 3D here. If we did some distance w into the page, we broke this up into a whole bunch of slices and integrated, blah 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 blah. If you did that, you would end up with the volumetric flow rate is equal to the following expression. You end up with rho g w h cubed sine alpha over 3 mu. And all of this makes sense too, right? The higher the viscosity, the lower the volumetric flow rate. the higher the density, the higher the volumetric flow rate, because basically we have more weight of fluid pushing down. Similarly, the more G, the more G, the more weight we're going to have, the more gravitational force we're going to have to pull that fluid down. More W, well, yeah, obviously it makes sense. If I scale W, I'm just scaling the whole overall system that flows. And interestingly, H cubed, so the volumetric flow rate very strongly depends on H. And we basically get, one factor of H just for having more area for that flow to go through, but also the higher the H, the higher the max velocity. And the higher the max velocity, the more flow rate we get. So we actually get an H cubed, partly from an area effect and partly from the max velocity scaling up with H. And then sine alpha, right, the more we tip up that plate, the more, the faster the flow is going to be going down. So the more volumetric flow rate we get. So what does this mean? We get, we've essentially accomplished our goals of deriving a velocity profile, using that velocity profile to help us get shear stress, or vice versa, and using that velocity profile to do something cool, like figure out volumetric flow rate. So I hope this has been a helpful presentation. Good luck with your studies of fluid mechanics. Bye.